Hey physics babies, welcome to Unit 6, Lesson 3. Today we're going to be talking about sound waves. Hopefully you enjoy our lesson today. There's a lot of information, so please make sure you are taking notes, but there's very little actual calculations and actual math that we need to do. So all of you that have hated my class all year because it's too much math, today's your day. By the end of the day today, you will be able to describe mechanical waves and understand sound waves in terms of intensity, pitch, resonance, interference, and the Doppler effect. So a mechanical wave is a wave that transfers energy through a matter medium. So we actually need something for the wave to go through. That something can be a solid, a liquid, or a gas. Doesn't matter, but it needs something. These waves cannot travel through empty space. Empty space is a vacuum, right? There's nothing in it, not even air particles. An example of a vacuum is outer space, in case you're like, I still don't get it. So these mechanical waves cannot travel through outer space, and they can be either transverse or longitudinal. A transverse wave is an example is a seismic wave, so an earthquake. And remember, that's the one that looks more like this. The longitudinal waves, an example is sound, is like this one, if that makes sense. And because these waves need a medium, that's why, you know, there's that saying about like, you scream in space, no one can hear you, because the sound literally cannot travel through a vacuum. Kind of cool. So sound waves, mechanical longitudinal waves that are caused by vibrations that push particles around. So we can see here, remember it's longitudinal, so we've got these compressions and rarefactions. Compressions when the particles are really close together, rarefactions as they kind of spread out. And the vibrations, typically we experience them through air, push air particles around, and that's how we get sound. So we're gonna start talking about all these different properties of sound waves. The first one is intensity. So intensity is really just how loud the sound wave is. We use decibels to measure that in, and that's lowercase d, capital B. Intensity is really just how much energy that wave has. The more energy, the louder that wave will be to us. So looking at this, our threshold of hearing, we start at 0 decibels, and our threshold of pain is about 120 decibels. So that means at 0 decibels, we can start hearing things. And at 120 decibels, it's actually going to be painful for us to experience that sound. So looking at this, we've got rustling leaves at about 20 decibels, whereas a noisy restaurant is at about 80 decibels. And think about it, if you were to experience, you know, gentle rustling leaves as you walk down the sidewalk versus sitting in a noisy restaurant, which one's louder? Past 120, things are actually painful, and that's why we need to be really careful when we're blasting our music in our headphones. You can actually start to damage your ears, and that will cause this threshold of pain to get lower and lower and lower. A jet plane taking off is at about 150 decibels, and that's why if you've ever been to or just like seen, you know, like the jet plane shows where they like zoom around and like they use their trails to like make patterns and stuff. Everyone's got earplugs in, and everyone's got those earmuff deals that actually block out the sound on. It's to protect your ears because 150 decibels is painful. So there you go. Next thing we're going to talk about is pitch. So a pitch is determined by the frequency of the wave, and we use hertz again to talk about pitch. So humans, our auditory field, we hear between 20 hertz and about 20,000 hertz. Cats and dogs, on the other hand, they start a little bit higher, but their hearing goes all the way up to 40,000 hertz. That's why if you've ever like seen people, you know, with the dog whistle, right? They blow it and we don't hear anything, but dogs freak out. It's because that whistle operates in between 20,000 hertz and 40,000 hertz. Some other, you know, examples, bats and dolphins are obviously operating and able to hear much higher frequencies than humans, whereas elephants and moles are actually able to hear sounds that are at lower frequencies. Down below, we have two waves. They have the same velocity, but they're operating at different frequencies because of their wavelengths. The wave on the left has a longer wavelength, so that means it's got a shorter frequency. Whereas this wave on the right, there we go, same speed, but a shorter wavelength, so it has a higher frequency. A higher frequency tends to be a higher sound, whereas a lower frequency is a lower sound. So pause me, go to this website. Use your headphones and begin with your computer at a lower volume so you're not damaging your ears. And I want you to take a second, go through it, and actually write down the first frequency that you can no longer hear. As you finish the video, it's quick and it's actually pretty interesting, but it's honestly pretty accurate. I just turned 25 in December, and as soon as it hit that like 24 and under, I was like, yeah, no, I can't hear that anymore. So kind of cool. Let me know. Oh, I'm sorry, I changed this website. It's just a hearing test. Let me know what it is, but there are actually specific sounds, like it's about 1800, I believe. And anything higher than that, like if you're above 24, you can't hear. So I wasn't able to hear it. It's kind of cool. Let me know where yours is at. And as you damage your ears with things like loud music, Ricardo, looking at you, you're actually damaging your hearing, and so you won't be able to hear those high-pitched noises anymore. All right, next up is interference. So an interference is two or more waves that overlap to form a new wave. So in this picture, we've got two waves coming towards each other. One is small, one is large. When they meet in the middle, they overlap and they're actually growing, and then they continue moving on their way. That is an example of constructive interference. Constructive interference, we end up with a larger wave when they overlap. We kind of add them together. So as you can see here, we've got wave 1 in yellow. Wave 2 is blue. And when we add them together, we get the green wave. It's larger than either of those waves were individually. But if there's constructive, what else do you think there is? Destructive. So in destructive interference, we actually wind up with a smaller wave initially. So we've got wave 1 in yellow, wave 2 is in blue. And when we add them together, we're still adding the waves together, we get a smaller wave in green than we would have with either wave by themselves. So make sure you dot in these little examples so you can kind of see the difference. The key with constructive versus destructive, though, constructive interference, you're going to wind up with a large wave because the crests add together to make a larger crest. The troughs add together to make a larger trough. In destructive, we've got a crest and a trough. So if I've got something high and then something low, when they kind of come together and add them up, we get a smaller number. It's like adding a positive and a negative number. You wind up with a smaller value. So there we go. And then this is just an example. We've got the blue wave and the green wave. The purple wave is the interference pattern. So as the waves go through each other, we can see how the purple wave can get really large when those two waves add together, and it can get really small when the two waves kind of cancel each other out. We've got that destructive interference. All right, standing waves. So a standing wave is just that. It's a wave that appears to stand still. You don't need to know much about standing waves, but you need to know that the node is the portion that does not move, and the antinode is the crest and trough portion. Please go to this YouTube video. It's like 4 minutes. Watch it so you can actually see what a standing wave looks like in reality. I was going to do a demo of this, and now, you know, quarantine. So watch their video. It's cool. Take a couple notes to make sure you fully understand what a standing wave is. All right, resonance. So this is like the part that I'm really excited about. So Resonance is the tendency of a system to oscillate at certain frequencies and wavelengths. All objects naturally have a frequency that they tend to vibrate in. This is called their resonant frequency. Remember, all objects are made up of atoms, and atoms are vibrating, they're moving, okay? And so this is that resonant frequency. If we have a wave that matches the frequency of the object, so the wave has a frequency, the object has a frequency, they're the same frequency, we get resonance, okay? Resonance is the amplitude of an object's oscillations are increased by the matching vibrations of another object. A very complicated way of saying that because these frequencies match, we actually get a larger amplitude in our wave. The amplitude, remember, is the distance from the crest or trough of a wave to that midpoint. By having the same frequency, that amplitude gets larger. All right, I actually have some examples. Yeah, I have some examples, so hold on. So the example that we're gonna use here is, if you've ever seen people with a wine glass and they like play the wine glass, hold on, So if you have a crystal glass, you add water to it, you can play it, all right? And it sounds really pretty, especially if you have talent, which I don't. But we're rubbing the glass, and we're rubbing the glass at the frequency that this glass naturally wants to vibrate in. Adding water changes the frequency that the glass wants to vibrate in. If we add more water, we get a lower note, which means we have a lower frequency. If we take water away, our note is going to get higher, which means we have a higher frequency. And if you were really aggressive with it, you could actually get the glass to vibrate to the point that it will shatter because you reach like that perfect resonance frequency of your glass. Pretty cool, huh? All right, back to our, oh no, one more thing I want to talk about. If you go online, you will see in Google Resonancy, it will talk about the Tacoma Narrows Bridge. It's a really cool story. You should check it out. Basically, they spent all this money building this really, really long bridge, did a bad job of it. The bridge was in service for like 4 months before a huge sustained gust of wind, essentially caused the whole bridge to like sway and actually break. Huge crash, huge devastation. Only casualty was a dog, so that's good. But they say it's resonance, it's not resonance, so you know better. But check it out anyways, it's a really cool engineering disaster. All right, moving back to our PowerPoint. So, speed of sound. Here's where we might start having a little bit of calculation, so don't panic. The speed of sound in air is 343 meters per second. For reference, that is 768 miles per hour. Sometimes the speed of sound is talked about in Mach speed. Mach speed just means you are moving at or faster than the speed of sound. Mach 1 is exactly the speed of sound. If you are supersonic, you are going faster than the speed of sound, and that's what creates a sonic boom. Check it out, it's crazy loud. And so because you are traveling faster than the speed of sound, the way the sound waves pile up as you are traveling creates that boom. And you can actually kind of see it right here, pretty cool. So make sure though, big thing, note that speed of sound is 343 meters per second. Remember, if we are calculating the speed of a wave, we multiply the wavelength by the frequency. So V equals lambda times F. V is the velocity, lambda is the wavelength, F is the frequency. If we are talking about a sound wave, what's its velocity? 343 meters per second. Excellent. I do want to be clear, this 343 meters per second, it's for a very specific temperature. Temperature changes the way particles can move, just as like a caveat, but you only need to worry about 343, okay? Okay. So here's our one calculation. We've got a sound wave in air that has a frequency of 21,000 hertz. We want to calculate its wavelength. First question, 21,000 hertz. Can a human hear at 21,000 hertz? Nope, hopefully you said no. Okay, let's do it though. So we've got this right here is our frequency. If it's a sound wave in air, we know its velocity is what? 343. Beautiful. We want to calculate the wavelength. So we're going to use that formula, V equals lambda times frequency. So 343 equals lambda times 21,000. To get our lambda all by itself, what are we going to do? We have to divide both sides by 21,000. I picked division because we have multiplication, and division is the inverse operation. Those go away. We are going to use our handy dandy calculadora. 343 divided by 21,000. And I got that our lambda is 0.0163. What do we measure wavelength in? Meters. Okay, 3 sig figs is fine. Make sure you include your units. Hopefully you're feeling pretty good so far. All right, last thing we're going to talk about is the Doppler effect. And you have experienced the Doppler effect without actually realizing that you have. So the Doppler effect is the apparent change in the frequency or pitch of a sound that's caused by motion. Now, this motion can either be the person listening or the source of a sound. If the sound is moving towards you, it sounds higher pitched. And when the sound moves away from you, it sounds lower pitched. The easiest example of this is police and ambulance sirens, right? As they kind of come towards you, they sound really high. And as soon as they pass you, that sound gets a lot lower in pitch. It's the Doppler effect. These sound waves kind of start stacking up because of the object in the way, right? Because sound waves need a medium to travel through, right? So the object is moving, the sound waves start stacking up because they're being pushed forward, and that gives you a higher pitch, a smaller wavelength, higher frequency. And then as the object passes you, they're able to kind of spread out again, and that's where we get that longer wavelength and lower frequency. Another example of the Doppler effect is actually in astrophysics, and this is why I think it's so cool. So our universe is constantly expanding. Objects that we view that are moving away from us are redshifted, because red is a longer wavelength of light. So whatever light that thing is emitting looks more red than it actually is. Objects that appear to be moving towards us are blue shifted, so they appear more blue than they actually are. Kind of cool, and that's how we can see and kind of track where things are in the universe and what direction things are moving, because we look at that shifting wavelength of light. All right, that's it. I hope you took a lot of notes. The assessment on this is going to be pretty straightforward. I think we've got like one calculation and then just some questions that are more vocab based and concept based. So if you have any questions, feel free to reach out. I'm available via email, via Google Phone during office hours. You can comment on Google Classroom, whatever works best for you, but I'm here for you. That's it. I love you all lots and do great things. Bye.